Welcome back to Science Corner,
Uh,
to our deep dive series for the intellectually curious amateur scientists out there.
Sounds good.
Today we're going to be embarking on a pretty fascinating exploration, I think,
Okay.
into the world of the dragon curve.
Right.
You might have encountered intricate self-repeating patterns before,
Right.
but the dragon curve, I think, holds a particular elegance and appears in some really surprising places.
Yeah, the dragon curve is really a quite remarkable mathematical object.
Yeah.
It's a fractal, meaning it exhibits self-similarity
Right.
at different scales, and it arises from a very simple iterative process.
Okay.
What makes it so compelling is its blend of simplicity
Yeah.
in its creation and the complexity of the forms that it generates.
Yeah.
And it pops up in all sorts of areas, ranging from paper folding to very abstract mathematics.
Absolutely. And who better to guide us through the intricacies of this mathematical dragon than a Nobel laureate, whose work has in part touched upon this fascinating realm of fractal geometry. Welcome to the show.
It's a pleasure to be here.
Okay, let's start with the most well-known member of this family, the highway dragon.
Yeah.
Now, this wasn't some purely theoretical exercise, was it? Our sources indicate it has roots in some rather practical scientific endeavors.
That's right. The Highway Dragon was first investigated by NASA physicists John Highway, Bruce Banks, and William Harder.
Wow.
They encountered it in their work, and it was Martin Gardner who then introduced it to a wider audience
Okay.
through his mathematical games column in Scientific American back in 1967.
So this has been around for a while.
It has. Following that, mathematicians like Chandler Davis and Donald Knuth further explored its mathematical properties in detail.
Okay.
And it even gained some popular recognition through its appearance on the section title pages of Michael Crichton's novel Jurassic Park, which is a rather unusual place to find a sophisticated fractal.
A fractal gracing the pages of a dinosaur thriller. That's certainly a memorable connection. So for our listeners who are eager to visualize this, how do we actually construct the Highway Dragon? Let's start with the very basics.
We begin with a simple line segment.
Okay.
The construction is recursive. Imagine taking this segment and replacing it with two new segments of the same length, joined at a right angle.
Okay.
Now, the crucial part is the orientation.
Right.
With each subsequent iteration, as we replace every existing segment with this right angle shape, we alternate the direction of the turn by 45 degrees, first to the right, then to the left, and so on.
So the very first step transforms our straight line into a sharp 90-degree bend.
Exactly.
Then in the next step, each arm of that bend is itself replaced by another 90-degree bend.
That's right.
But one will be angled 45 degrees clockwise relative to its parent and the other 45 degrees counterclockwise.
That is exactly right. If you consider the image provided in our materials, you can see this iterative process unfold. The initial steps are quite straightforward, but as you progress to, let's say, the 9th iteration, the intricate dragon-like form, with its characteristic twists and turns, becomes clearly visible,
Okay.
and the self-similar nature begins to emerge. What's remarkable is how such complexity arises from this very simple rule applied repeatedly.
It truly is. Now, for those of us who appreciate the language of mathematics, our sources also present a way to define the Highway Dragon using something called an iterated function system, or IFS. This involves complex numbers, which might sound intimidating, but it's actually a very elegant way to capture the essence of the fractal.
That's right. In the complex plane, the Highway Dragon is what is known as the attractor
Okay.
of two affine transformations,
Right.
1 plus IZ2
Yep.
and SEZ11IZ2.
Okay.
You can think of these as two simple rules
Okay.
that operate on points in the complex plane. If you start with just a basic set of points, say just 0 and 1, and you repeatedly apply these two functions to every point in that set,
Yeah.
the resulting collection of points will progressively fill out the shape of the Highway Dragon.
So it's like you're taking these two equations and they're like rubber stamping the dragon onto the complex plane?
Yeah.
Okay.
It boils down this complex geometric construction into just two simple algebraic transformations.
Okay.
And this allows us to analyze the curve
Yeah.
using the very powerful tools of complex numbers and linear algebra,
Yeah.
revealing properties that might be hidden in the iterative geometric approach.
That's a powerful way to think about it, reducing a complex shape to a couple of equations. And for those who prefer working with real numbers, our sources also mention a matrix form of this IFS.
Right.
How does that relate to the complex number definition?
For those who are comfortable with linear algebra, These transformations can also be expressed using matrices,
Okay.
operating on pairs of real numbers, x, y, which represent a point in the plane.
Yep.
X corresponds to a rotation by 45 degrees counterclockwise,
Okay.
followed by a scaling by a factor of 1, 2.
Okay.
The second transformation, XX, involves a rotation by 135 degrees counterclockwise, the same scaling by a 1, 2, and then a translation by 1 unit in the x direction.
Okay.
These matrix forms essentially encode the rotation, scaling, and translation operations
Gotcha.
in a different mathematical language, making it easier to perform these transformations computationally and connect them to concepts in linear algebra.
So whether we're visualizing it step by step or defining it with these sets of equations, we have a clear picture of how the highway dragon is constructed.
Right.
But the story goes that its discovery wasn't through abstract equations, but through something much more hands-on, folding paper.
Yeah,
That's a wonderfully intuitive way to stumble upon such a sophisticated mathematical object.
it's a beautiful example
Yeah.
of how mathematical concepts can arise from very everyday activities.
Right.
The highway dragon was discovered
Yeah.
by repeatedly folding a long, thin strip of paper in half, always folding in the same direction, say to the right.
Okay.
If you then unfold the paper, and at each crease make a 90-degree turn,
Okay.
the sequence of turns you make, right or left, corresponds exactly to the sequence of segments in the iteratively constructed highway dragon.
That's incredible. Can you give us a sense of what those turn sequences look like for the first few folds?
Certainly, if you fold the paper once to the right and then unfold it, you'll have one right turn.
Right.
So the sequence is simply R.
Okay.
If you fold it again to the right and unfold, the sequence of turns is RRL.
Okay.
A third fold gives you RRL, RRRL, and a fourth yields RRRRRRRRL.
Oh, wow.
You can start to see a pattern emerging in these sequences of right and left turns.
Yeah, and there's a recursive rule that governs how these R and L sequences are generated with each additional fold, isn't there?
Yes. Each iteration sequence is formed by taking the previous sequence, appending an R, and then appending a reversed copy of the previous sequence where all the L's and R's are swapped.
Fascia.
This recursive rule perfectly mirrors the geometric construction of adding two segments at a right angle in alternating directions.
Okay.
Of course, as anyone who's tried to fold paper multiple times knows,
Mm-hmm.
you quickly reach a practical limit
Right.
where the paper becomes too thick and unwieldy to fold sharply enough
Yeah.
to perfectly represent higher iterations.
I can only imagine the thickness after, say, 9 folds. So we have this fascinating curve
Yeah.
with its unique construction and surprising connection to paper folding. What are some of its key properties that make it so interesting and important in the world of mathematics?
Well, one of the most striking features, as we touched on earlier, is its self-similarity.
Oh, yeah.
Imagine you take a magnifying glass to any sufficiently large part of the dragon curve.
Yeah.
You would see a smaller version of the entire dragon, often tilted by 45 degrees.
Okay.
This self-similarity repeats at infinitely smaller scales.
Wow.
And the scaling factor between these copies is always the square root of 2, a fundamental mathematical constant that appears frequently in this context.
Okay.
This self-similarity is a hallmark of its fractal nature
Yeah.
and leads to the intriguing property that many of its lengths, when appropriately scaled, are simple, rational numbers.
It's like the mathematical equivalent of those Russian nesting dolls, but with an infinite level of detail. And I understand that these dragon curves aren't solitary creatures.
Right?
They can actually fit together to tile the entire plane without any gaps or overlaps.
That's right.
That seems counterintuitive for a line-like curve.
It is a remarkable property.
Mm.
One way to visualize this tiling is to consider a standard grid of squares covering the plane, like a checkerboard.
Okay, like a checkerboard.
If you then replace each edge of every square with a segment of the dragon curve oriented according to the color of the square it borders,
Okay.
these dragon curve segments will interlock perfectly, completely filling the two-dimensional plane.
So despite looking like a one-dimensional curve, winding and folding, because it can completely cover a two-dimensional area, it has a fractal dimension of exactly 2.
That is exactly right.
That's quite a leap from the dimension of a simple line, which is 1.
In this context of space filling through tiling, its fractal dimension is indeed 2.
Okay.
And as a consequence of this tiling property, if you consider a highway dragon constructed from an initial segment of length 1, the total area it encloses when it tiles the plane turns out to be exactly 12. Surprisingly clean and elegant result.
That is a neat and unexpected value.
Yeah.
Now, what about the boundary of this area filled by the dragon curve?
Right.
That edge must be incredibly convoluted.
The boundary is indeed very intricate. It has infinite length,
Okay.
constantly folding back upon itself.
Yeah.
Its fractal dimension, which quantifies its roughness or complexity, is approximately 1.5236.
Okay.
The fact that this dimension is between 1 and 2 tells us it's more complex than a simple curve, but doesn't completely fill a two-dimensional area in a smooth way. Interestingly, this value is related to the real solution of a specific cubic equation, the log O2 EO2, where the fractal dimension is given by 2 log O.
Oh, wow.
The exact value of 2 involves cube roots, and it's a bit complex to express simply.
Sure.
But this connection highlights the deep algebraic underpinnings of this seemingly geometric fractal.
So the dragon itself is a two-dimensional space filler,
Yeah,
but its edge has this fractional dimension making it wigglier than a straight line, but not quite a filled area itself.
that's right.
Fascinating. Now, the highway dragon is clearly a star player, but our sources also mention that it's not the only dragon in the mathematical kingdom.
That's right.
There are other dragon curves.
That is correct. The dragon curve family is quite diverse,
Okay.
with various members exhibiting their own unique properties and construction methods. One notable relative is the twin dragon, also known as the Davis-Knuth dragon,
Okay.
named after the mathematicians who studied it extensively. As its name suggests, it can be visualized as 2 highway dragons placed back to back, with one being a mirror image of the other.
A sort of Siamese twin of the highway dragon.
Precisely.
Okay.
Its IFS definition is very similar to that of the highway dragon,
Okay.
but with a slight modification in the second transformation.
Wow.
S 1 plus IZ2 and S is 1 plus IZ2.
Okay.
The initial set for the IFS also includes an additional point, typically 0, 1, 1I.
Okay.
The twin dragon also has an elegant description using L systems,
Okay.
which is a formal grammar where you start with an initial string of symbols
Okay.
and apply a set of replacement rules iteratively to generate increasingly complex strings, which then correspond to the sequence of movements to draw the curve.
Gotcha.
Interestingly, the twin dragon has connections to complex base number systems where the base is -1
Wow.
showing a surprising link between number theory and fractal geometry.
It's amazing how these seemingly disparate areas of mathematics can intertwine. What other draconic forms are out there in this mathematical bestiary?
Well, we have the tear dragon, which is constructed by iteratively replacing a line segment
Okay.
with 3 segments of the same length,
Okay.
each connected at 120-degree angles, forming a kind of zigzag.
Okay.
Its L system definition is quite simple. Start with a single F, representing a forward step.
Okay.
And the rule is to replace every F with F plus FF,
Okay.
where plus and dec denote turns of plus 120 and negative 120 degrees, respectively.
Okay.
It also has an IFS definition
Okay.
involving scaling by 12
Gotcha.
and rotations by 120 and negative 120 degrees involving complex numbers,
Okay.
with a factor of F 12,823 and its complex conjugate. Okay.
And I recall seeing a mention of the Levy dragon in our sources.
Right.
Is that another member of this family?
Yes, the Levy-C curve is sometimes informally referred to as the Levy dragon.
Okay.
It's another fractal curve constructed iteratively by replacing a line segment with 2 segments of equal length joined at a right angle.
Similar to the basic step in the highway dragon's construction. But the arrangement of these segments is different.
It's quite a diverse and fascinating family of curves,
Yeah.
each with its own unique characteristics and construction.
Right.
Now, we've explored their intrinsic mathematical beauty, but you mentioned earlier that the dragon curve appears in unexpected places beyond just looking intricate. Could you elaborate on some of these connections to other areas of mathematics or even science?
One intriguing connection
Okay.
arises in the study of solution sets
Okay.
of linear differential equations.
Okay.
The principle of superposition in linear differential equations, where combinations of individual solutions are also valid solutions,
Yeah.
shares a conceptual similarity with how iterated function systems generate complex sets
Okay.
by iteratively applying transformations to simpler initial sets.
Yeah.
It's a beautiful example of how similar underlying mathematical principles
Right.
can manifest in seemingly different fields. That's a rather profound link. And I also came across information in our sources about a connection between the dragon curve and Littlewood polynomials.
Right.
That sounds quite abstract. Can you shed some light on that?
It is a fascinating connection that bridges fractal geometry and the theory of polynomials.
Okay.
Littlewood polynomials are polynomials where all the coefficients are restricted to be either +1 or gain 1.
Okay.
And there's an iterative way to generate sequences of these polynomials
Okay.
using two simple functions. SZ, 1 plus yarrow, and fes0 by e20 by a20 by a20 by 8b's, where WBZB is a complex number with a magnitude less than 1.
And where does the dragon enter this polynomial picture?
If you specifically choose the value of W to be 1 plus I2,
Okay.
you'll find that these two polynomial generating functions become mathematically equivalent
Okay.
to the two affine transformations.
Okay.
That define the IFS of the highway dragon.
Gotcha.
What this implies
Okay.
is that if you iteratively apply these polynomial generating functions, starting from what's called a zero polynomial,
Okay.
the set of values you obtain by evaluating these polynomials at ZW1 plus I2 at a certain degree corresponds precisely to the set of points that form the highway dragon at a corresponding iteration.
Okay.
And furthermore, when mathematicians plot the roots, the values of z for which the polynomial equals 0
Yeah.
of a large number of Littlewood polynomials, they've observed the emergence of very intricate structures
Okay.
in the complex plane that bear a striking visual resemblance to the dragon curve, particularly near the coordinate corresponding to W1 plus I2.
So this complex and beautiful fractal pattern is somehow encoded within the roots of these polynomials with such simple coefficients?
That's right.
That's an incredible connection, highlighting the deep interconnectedness within mathematics.
It is.
It's as if the dragon curve is a hidden geometric signature within these algebraic objects.
The dragon curve serves as a remarkable bridge linking geometry, algebra, complex analysis, and even computer science through its recursive definition.
Wow.
And its description using formal systems like L systems. It underscores how seemingly abstract mathematical objects can have surprising and far-reaching connections.
This has been a truly enlightening exploration.
Yeah.
We've journeyed from the simple act of folding paper
Right.
to the abstract world of complex numbers
Yeah?
and polynomials,
Uh-huh.
all connected by this fascinating dragon curve. We've seen its construction, its surprising origins, its intricate fractal properties like self-similarity and space filling, and its unexpected links to other mathematical domains. It's quite remarkable how such a rich and complex structure can arise from such a basic iterative rule.
Indeed. It's a testament to the power of recursion and the inherent beauty that can emerge from the repeated application of simple transformations.
So for our listeners, the next time you find yourself idly folding a piece of paper, take a moment to appreciate the hidden mathematical elegance you might be creating. Perhaps even try to visualize the first few iterations of the dragon curve in the creases. And thinking more broadly, consider how other seemingly simple iterative processes, whether in mathematics, nature, or even the algorithms that power our technology, might be generating similarly complex and unexpected forms all around us.
Right.
What fundamental principles of self-similarity and recursion might be at play in shaping the world we see? Thank you so much for sharing your profound insights with us today. It's been a truly captivating deep dive into the draconic world of mathematics.
My pleasure. It's a journey of discovery that never ceases to fascinate me.
It's been great having you on.
Thank you.
Till next time.